The next speaker is Kensuke Gallock Yoshimura, title Harvesting Mutual Information from BTZ Black Hole Spacetime. Please.
All right. Thank you for the introduction. So this project was done by me and Robert Mann and two undergrad co-op students, Lucy and Kendra. And you can find our paper on either arXiv or the PRD. So this project is about harvesting correlation. And I know many of you know about entanglement harvesting, so but I will just briefly go through what it is. So entanglement harvesting is something like this. You have curved space-time, and on top of it, you have like a scalar field, and you prepare two particle detectors. And typically, we use Unruh-DeWitt detectors, and we let them interact locally with the field. And what will happen is that at the end of the interaction, they'll become entangled. So two detectors will be entangled. This is because the quantum field is already in entangled state, even in a vacuum. So basically, what this is pretty much extracting entanglement from the field. So we call this entanglement harvesting. And in general, you can harvest other types of correlation from the field. So I will just call them like correlation harvesting. And in our paper, we are interested in correlation harvesting in black hole, BTZ black hole space-time. And in particular, we looked at mutual information. Okay? And mutual information is basically the total correlation, including entanglement. And in particular, this entanglement harvesting scenario was done by Laura Henderson and her collaborators. And in their paper, what they found was that near the event horizon, there is the region called entanglement shadow, where you cannot harvest entanglement at all. Okay? So in our paper, we looked into this mutual information harvesting and see what happens to this shadow and examined why this is why this shadow exists. Okay? So to begin with, let's look at, well, let's review BTZ black hole space-time. So BTZ black hole space-time is 2+1 dimensional space-time, which has negative constant curvature. And the metric is given by this guy. And throughout this talk, I will consider two static detectors outside event horizon. And the detectors are two-level quantum system with ground in excited states with energy gap omega. And they interact with the field like with this Gaussian switching function. And I'll write dA or dAb as a proper distance between 2 points. So in this case, dAb means proper distance between detectors A and B. And in particular, we will fix dAb and we change the value of dA. Okay? So in previous paper done by Laura and her collaborators, what they found was that if you plot the amount of entanglement extracted from BTZ black hole space-time as a function of dA, so the proper distance from the event horizon, then you will get something like this. Okay? This curve means that if you are if the detectors are far enough from the black hole, then you get some entanglement. However, if the detectors are too close to the event horizon, then you cannot harvest the entanglement at all. So this region that of zero entanglement is called entanglement shadow. Okay? So the reason for this entanglement shadow, they gave two reasons. One is gravitational redshift, and the other is high Hawking temperature. So intuitively, near event horizon, there will be extreme Hawking radiation attacking the detectors. So it is too noisy to extract entanglement, and also the gravitational redshift dilutes the correlation between detectors. Right? So in our paper, our interest was which one, either gravitational redshift or Hawking radiation, right? Which one actually kills the correlation near the black hole? And to see this, instead, we looked at something called mutual information. Mutual information is the total correlation, including classical and quantum correlations. And we determined, or we looked at the effect of Hawking temperature and the redshift by writing mutual information as a function of them, and see how mutual information gets killed. Okay. So first of all, let's look at how mutual information behaves outside the event horizon. So again, I put this diagram of two detectors outside the event horizon. And if you plot mutual information here, then you can see that the correlation dies near the event horizon. And in particular, at the event horizon, the correlation dies. So no one can harvest anything. And the question is, why does this happen? And in next slide, I will show you that it is not gravitational redshift, but it is Hawking radiation that actually kills this correlation. Okay? So to see this, what we did is that we wrote mutual information, IAB, as a function of local temperature and redshift of detector A, the closest to the event horizon. And we fixed either temperature or redshift factor and changed the other variable. Okay? So first, let's look at the case where temperature is always constant. In this case, you can easily check that it corresponds to a scenario where the proper distance of the detector is always fixed, but the size of black hole changes. Okay? Then you can plot mutual information as a function of redshift factor. And this figure shows that for any value of redshift factor, mutual information never dies. Okay? So from this, we conclude that it is not redshift factor that kills mutual information. On the other hand, if you fix the redshift factor and change temperature, what will happen? In this case, it corresponds to detector. So if you want to look at low temperature regime, you want to put the detector really far away from the event horizon of small detector, small black hole. And if you want to increase the temperature, then you need to put the detector really close to the event horizon of a huge black hole, right? So in this case, we also plotted the mutual information as a function of local temperature of detector A. And you can see from this figure that as the temperature increases, the mutual information dies exponentially. Okay? So we concluded that it is extreme Hawking temperature that actually kills the mutual information. Okay. So in summary, we have investigated the correlation harvesting in BTZ black hole space-time. In particular, we looked at this the total correlation mutual information, and we saw that it dies at the event horizon. But it is not gravitational redshift, but it is Hawking radiation that actually responsible for this death of correlation. And we expect that this is true, also true for the death of entanglement near the event horizon. Probably I'm a bit too early, but this is my talk. Thank you very much.
Thank you very much. We can take up to one question if there is one. Albert.
Yes, so I mean, it's just a matter of terminology mostly, but I guess sometimes people would make the distinction and say that the radiation you were considering would really correspond to acceleration radiation rather than Hawking radiation.
Yeah.
I mean, just because you're close, but also because you could think of examples where you could kind of naturally distinguish both of them, for example, far from the black hole, and it would probably be closer to what one would call acceleration radiation, right?
Yeah. So in BTZ black hole case, you can actually decompose into ADS Linder, which is the acceleration part, and pure BTZ part. And for actually, yeah. So sorry. Yeah, and I believe that by decomposing two factors, it is BTZ contribution that actually kills the mutual information. So does it answer the question?
Yes, I'm not sure. It does answer my question. I'm not sure I understand the answer 100%, but okay. So you're saying that it's very close to the horizon is the BTZ part rather than the acceleration part when you have this natural decomposition of the two, if I understood correctly, right? That's what you said. If I understood correctly. Somehow I was not expecting that answer, but I guess we can leave it for the discussions session.
Like a good topic for the joint discussion time. So thank you very much again.
Right, thank you.
Maybe it's a matter of terminology, this distinction between the contribution from acceleration radiation and Hawking radiation in various,
so
in particular in BTZ.
Yeah, I can clarify quickly. So it turns out, yeah, both acceleration radiation and Hawking radiation matters. So if you look at like this figure, blue is BTZ part, so it's black hole contribution, and red one is acceleration radiation. Okay, so if they're zero, that means you know, the correlation gets killed, and orange is the sum of them. Okay, so Hawking radiation contribution actually dies very quickly, and after that, acceleration radiation gradually becomes to zero. So in that sense, both radiation will, you know, contribute to this death of mutual information.
So can you remind me what was the x-axis here? So when you say it dies, it's a function of
the local temperature of detector the closest to the event horizon.
So it's the temperature times
Oh, sigma is the typical duration of interaction. So we are using Gaussian switching. So
okay, and this is the temperature that somehow the detector would measure at the detector position.
Yeah.
And so when it increases, then in some sense, acceleration radiation is more important. Although one could also think of that as being closer to the horizon or not, and so on. Okay. Yeah, I mean, well, I'm not sure whether I'm interpreting that correctly, but I guess I would probably expect that if I move away from the horizon, I will eventually be dominated by Hawking radiation rather than acceleration radiation. So I know the variable here is a different one, but I'm not sure whether one could relate it in that way.
Yeah, so in this case, high temperature means it is really close to the event horizon of huge black hole.
Yeah.
Yeah.
Somehow the intuition I had was that their radiation temperature would dominate. Acceleration radiation would dominate. That would be my naive intuition, and your plot seems to agree with that, I think.
In near horizon.
Yes, so that near horizon radiation, acceleration radiation would dominate that, in vice versa, far from the horizon. So I think your plot, if understood correctly, even though it's not plotted in exactly that way, but seems to agree with that, I believe. So,
okay.
So you're saying that high temperature means getting close to the horizon, and so there I would expect that the acceleration radiation dominates. But maybe it's also part of a problem of how one defines the separation between acceleration radiation and Hawking radiation. So
okay.
Okay, good.
Thank you.
Thank you.